electronics and telecommunication engineering, and he made a switch to climate sciences, bringing in a different flavor along with him, different set of tools, understanding, and he's applying them as you'll see. So let's welcome Angshuman.
Hello everyone. So homework time. Did everyone did the questions that I asked? Did you solve that one? When the satellite goes behind is in the Earth's shadow. Did you get the answer? Cool. Very good. So let's. I have asked few other things like with n layers, what the system will look like, right? So what will happen if you have, let's say, 100 layers or 50 layers? Huh? Okay. So if you keep on increasing the number of layers, what will happen? What does the function say? It's a simple linear function. Huh? It will keep on increasing, right? So that's why we needed something, right? Because it was a completely black body that we have assumed, but that was not the case. That is not the case, right? We have also seen only some fraction of the energy will be absorbed and rest will go to the space directly from the surface. We also had that. So today I will build from the final simple model that I showed you, where there was a sense of time, and that is how all these IPCC reports or any climate change paper, if you see, if they want to project the future warming, they need this thing called climate feedback, and we had a simple linear equation, right, where you had this lambda, which is the climate feedback. So based on that, I thought of giving you this, the inconstant nature of climate feedback and climate sensitivity. Why inconstant? We already know that lambda depends on several other things, and we are going to see, I'll give you very quick examples on that. So this is the model that we have seen, which is a widely used model. C is the global heat capacity. Here again, it has to be delta T, not just T. This is the radiative forcing. This is lambda, and this is again the delta T. So this, how can we measure delta T? How do you measure delta T? I mean, simple thermometers, right? We can use thermometers to do that. How do you measure the radiative forcing here? F. Okay, so we will see that. And this is as Nihar pointed out yesterday, what does this C represent? So it is primarily the heat that is going into the ocean. And also in the energy flow diagram, we have seen that presently about 0.7 watt per meter square with a certain uncertainty is going into the system, into the ocean. So from here on, so we have seen also this one. So this is a very simple model. You know, this guy, Jonathan Gregory, for the first time, he showed that you can actually measure this delta, this lambda, just by a model simulation where you force the model with something and you wait for its response, and you then just plot the annual mean change in net radiative flux and change in surface temperature. People were using very complicated methods. By very complicated methods, I mean they used to run GCMs several times in different modes, on, off. Okay, you put this forcing, in the next one you don't put it. But in this case, he gave a very simple thing, and it turned out to be very good. Although if you calculate lambda based on this, the uncertainty is slightly higher. But what you do then, you can run those simulations maybe 2-3 times or 5 times, and you can take an ensemble of mean of that. But anyway, so just to praise Jonathan Gregory here, I have learned a lot from his papers. So this was the thing. So now in equilibrium, you can calculate the temperature change, and this is the feedback, and this is the forcing. So our primary aim in climate science, as I said, is the central problem to find this lambda value, because if you find this, you can predict the delta T. But for the current system, you know delta T, and let's say you can calculate F, then you can find lambda. And if lambda is the property of the climate system, so it should not change, right? So if it doesn't change, then you can simply plug in here, right? You can simply plug in here and you can calculate delta T. So that is the whole point. but it is really tough. So now for simplicity to talk to policy people, politicians and everyone, what they have defined some sensitivity parameter based on lambda called equilibrium climate sensitivity, which I have told you yesterday. And just the difference is that in place of F, which could be from anything, what they have done, this is 2 times CO2. And as I said, Arrhenius was the first person to show that, and he used a doubling CO2 scenario. So since 1896, people have been using it. Manabe used it in 1964 and later on, and so it is a custom to use double CO2. But right now in CIMIP 6, I mean in AR6, they are using in AR5, they have used quadruple CO2 just to see the difference between the signal and the noise of the climate system. So now, as I said, how do you measure this F? So there are, people have very good line by line radiation models, because people know the radiation has been studied from maybe before 1900s probably. So it is a well-known thing. So they use such line by line models to calculate F, and they come up with these simple expressions, empirical expressions, where you can calculate the forcing. But this is a single number that you'll get. So here, if you plug in, let's say C naught is a reference value. If you plug in here 380, and if you double it, so this will be 380 into 2, which will give you a simple number, which will be something like 5.35. Okay, so you get the forcing. Okay, for double CO2, the forcing should be something around this, simply from this. But it doesn't give you a spatial picture. What is the forcing over India? You don't know that. Okay, how much is the forcing? How does it look like? So for such things, you have to basically use these GCMs. You have to take the help of GCMs, and that's how GCM becomes an important thing in the science of finding the sensitivity and all. So this paper actually updated the previous ones, and they have given even better relationships. So this was to show you how F can be calculated. And this is the one that I was talking about. This lambda can be that can come from Planck's, that can be water vapor, lapse rate, surface albedo, and clouds. And when you sum them up, you get the lambda. So of course, because it's a complicated number, so let's divide it, let's segregate into different things, and then let's try to minimize the uncertainty in those measurements, in their estimates. So again, this was the simple model that I have introduced yesterday, but here now I have this scaling factor here, E, and this turns out to be 0.6 for our planet. And now if you differentiate this simple thing, you will come up with lambda here. And here, this SD alpha 4 DTS, this one is basically the albedo feedback. But both surface albedo, clouds, they are all actually contributing to this. But here, what I'm trying to say you, even though it's a very simple 0D model, but you get an idea of lambda, And this is the, primarily this is the water vapor feedback, but also lapse rate somehow comes here, okay, plays a role in the value of this. However, if you see this one, this is the Planck's feedback. And if you calculate, if you plug in TS to be 288 or 289, you get a number minus 3.25 probably. And you see the estimates from the GCMs, they are all something like this. So you can just appreciate, although it's a very simple model, but you get a very good match with that. So here I'm trying to tell you that how important it is to work with these simple models and build physical understanding. So here I've shown you this as well. So this is coming from IPCC AR6, and this is the net feedback, and the feedbacks that I was. Oh yeah, so here one E should be there. Yes, yeah. So I'm missing E here. Yes. This is like, you have to type in here, right? So it becomes a issue. So here now, the thing is, Planck is a negative feedback, and it is the only feedback which is trying to basically, keep our planet not going insane like Venus. And this is water vapor, lapse rate, they are positive feedbacks. So do you know what is lapse rate feedback like, and how it is different from Planck's feedback? This is also temperature. Lapse rate is also temperature, right? How it decreases with height, we talked. So it might happen that lapse rate is something like so the Planck feedback is talking about the uniform temperature, but how it varies with height, it is the lapse rate feedback that talks about. So this is surface albedo, this is the cloud. See, some of the models, some of the estimates, they say it could be negative, but most of them, they are saying it could be positive. It is positive. The mean value at least is positive. And this is something new that has come up in AR6. Here, now I have taken this figure from Block and Moritzen, where they have used radiative kernels. Okay, they have used, so they are something that will help you to basically calculate the individual feedbacks, as I was saying here. Okay, so this is for MPI ESM LR. This is 1.1, I guess. So this is the temperature feedback, and see, this is the Planck's feedback. So you can see wherever there is a very so let's look at the temperature feedback, and we can go on the others later on, maybe not. So here, why it is very dark? Who can tell me why it is very dark? See the color bar here. Why it is very dark there? It's a very simple thing. What is Planck feedback? You warm, it will radiate out just because of the temperature, right? So why it is dark here? Why the values are more, I mean, strong, the feedback is stronger there. Yeah, so more surface temperature. This is tropics, right? We have seen some of the plots, right, yesterday, that the tropics are much warmer. So it is because of that. And now then someone was interested in the surface albedo. So see, this is a very strong feedback here in the Arctic as well as in the Antarctic. And you know, to get a very good value of this, how they change, I guess what Vishak was telling, those kind of, you know, details has to be there in the GCMs. But GCMs again has this issue of computational power. You can only run up to a certain extent. In IISc, probably you can run few. In IIT Bombay, it is, you know, still we are developing our HPC systems. So it becomes a challenging thing. Only in certain places you can run all sort of simulations, and you need a lot of money. Okay, so going ahead and see, the most varying of all this feedback is the cloud feedback. Positive, negative, like it is a mix of all this. So that's why it is also the most uncertain one. Now, coming to the inconstant nature of feedback, which the title states. So the feedback depends or changes based on the forcing agent, how you force the climate system. It changes with the forcing magnitude, how by what magnitude you are basically forcing the climate system. It changes with time, it changes with the base climate. Okay. So here I show you a very simple example where it is a kind of both the forcing magnitude as well as the time is coming. So here in this figure, I show you again the Gregory plot, the regression for 2 times CO2, when you 4 times quadruple the CO2, for 8 times CO2 and 16 times CO2. And the slope is the lambda, right? The climate feedback that we have been talking about. And that is our aim. We need to know the number, single number, so that we can predict future warming. But you see, they are all changing. Here in case of 2 times CO2, why IPCC started avoiding 2 times CO2? Because you don't see, it's a single, it seems to be a straight line. But the moment you change the forcing magnitude, if you increase it, you see this bend. Okay, and in case of 8 times CO2, even there is a bend, right? So this bending shows you the impact of time on lambda. The other thing is, as you see, as you go from 2 times CO2 to 4 times CO2 to 8 to 16, there is also a change in the net slope. Now, let's say you have this, okay, and how do you calculate feedback? You have to draw a line, right? You can do linear regression, or also you just need 2 points to draw a line. What you could do, A very smart person, what he can do, because he doesn't know, he needs one number and he has to tell his people that no, I have this value. What he can do, he can just connect this point and this one. So it will be something like this, right? The line will be something like this, but that line will be very different from this steep line or this one. So that's how the forcing magnitude comes into play. Moving on. What happened? Yeah. So now, because of all this changing nature of inconstant feedback, okay, or the changing nature of the feedback, climate feedback. So Arrhenius, I told you that he said the warming for a double CO2 would be 5 to 6 Kelvin. Okay, the sensitivity was 5 to 6 Kelvin. It was his prediction more than 100 years ago. Okay, not a simple job to do. And then the first report, the Charney report came. Okay, there were several authors, and it was 1979. And you see the range of ECS, the equilibrium climate sensitivity that we have defined just now, is from 1.5 until 4.5. And then the first assessment report came from IPCC, which is around 1990. See, the range did not change, but the models have developed a lot. Okay. Then the second assessment report came, the range did not change. The third came, the range did not change. The fourth came, now they have to, because now people started to think what is happening. I mean, it is not changing, and we are just improving our models. We are including all the detailed physics in our model. But what is happening? So somehow they have used, mostly they have used models as well as observations to do this. But AR5, because people were not happy with this, they used only models, or yeah, probably only models, and this again. So it came back to this 1.5 to 4.5. So only in after this, in somewhere, I was a student then. So in WCRP, under WCRP, a lot of people, a lot of scientists all over the place, they met, sat together, discussed what can be done. Then they said that, okay, why not use different lines of evidences to constrain the estimate, to make sure, okay, what is not needed, let's just remove it. Okay, going through a negative logic, what we can remove. So in that fashion, they have reduced it. And the latest AR6 report, the likely range, all these are likely ranges. Okay, so the likely range is 2.5 to 4, which is smaller than all the previous ones. But the very likely range is also shorter, but again, it is still wider. Okay, so still more work is needed to really, like constrain or limit the uncertainty in ECS. But can anyone tell me why do you need to basically reduce the uncertainty? I have been telling it, but I want to know from you guys. Why do you need, why this is required? Why do you need to reduce? I mean, why we are worrying about this thing? Good for policy. I guess the other day, Shreyash and someone pointed out that how do you then tell the government that, okay, because if 4.5 Kelvin warming world is totally different. We have just warmed by 1.2, and we can see the heat waves in India. In my place, it is 42 degrees. It was never 42 degrees centigrade. So you can see, and it was just 1.2 here. Okay, so you can imagine if it is somewhere here, what would be the case? So that's why to give proper policy decisions, to make proper policy decisions, we need to, there is a need to do this. Okay. By the way, I forgot to mention, so Manabe and colleagues gave this 2 degrees centigrade for a double CO2, okay, which was again in the lower end of all this IPCC report. So I just wanted to quickly show you the over time how models have improved, and still we have that ECS range intact. Okay. See, initially the mid 1970s, you have only atmosphere, land, ocean, and sea ice. Very crude form. Okay. I guess Vishak will know more, and others will know more that how crude they were. But over time they have increased. So the cylinders, they are thickening, and they are also like darkening. So in all the cases. But only in after FAR, someone pointed out that something has to be there which should be balancing carbon dioxide or the greenhouse gases, because otherwise it should be only warming. But we are also seeing sometimes that there is a signature that there is something else which is basically cooling the planet. And then first time this aerosol people, who were doing aerosol science from long time, they came and they said that it is the aerosols. And I guess again in Sweden, I guess someone first bring in aerosol into the model, and then they started modeling that. And then the carbon cycle came in the concept of this Earth system models, dynamic vegetation. Vegetation was intact in one of this paper that we worked. The vegetation was intact. But had I have this model with dynamic vegetation, the results would be different. Anyway, so then atmospheric chemistry and then land ice. Also the time scale, as Vishal, many of Ashwin, a lot of people have already showed you that time scales also matter. So all these have different time scale. So now if you want the climate system to be in equilibrium, because we are talking about equilibrium climate sensitivity, the time scale is totally different. Now you have to run the model for even longer years. So again, the computation need is more. And I was planning to give you some detail about the models, but many of them have covered that the models have, these are the key ingredients: conservation of energy, the conservation of momentum, the Navier-Stokes. People have been talking about the continuity equation, not just on air, water, but also like water vapor, salt in the ocean, as he was talking about. The equation of state, a little bit of thermodynamics should be there. Equation for the formation of clouds, sea ice, and all. So these are the key ingredients for a climate model. Anyway, going ahead, and this is a typical picture of a latest Earth system model, MPI-ESM 1.2, where this is the atmosphere model. Okay, which people have been working a lot. So this got the largest space, and it has the ocean model. It has the land hydrology, dynamic vegetation, and the ocean biogeochemistry. And yesterday, Narita was talking about this flux coupler, right? So this is the flux coupler. So, and see how they are interacted. As I was saying, climate system is all these individual components and how they interact with each other. So this basically shows you that they are all interacting with each other. Even in the model, we have to model that. Okay, coming back to this, the slope of the regression tend to change. Forcing agent, it depends on forcing agent, the magnitude, the time with base climate state. And I'll give you some examples of forcing agent and time. So here in this slide, I'm showing you the dependence of lambda, which you cannot see because of this thing, dependence of lambda on the forcing agent. So now this lambda from that simple equation can be forcing by sun divided by the delta T, right? And this is forcing by CO2 by delta T. Lambda could be forcing by black carbon aerosols. You just somehow force the model with black carbon aerosols, and you calculate the temperature change, you get the lambda. But you see all those lambdas are different. See, so this red here is solar. Okay, the sun forcing. And the slope is different. The red line you see, and this is the black line for the CO2. Here, again, you see black carbon is very, it has a very clear signal that it is very different. And as I was telling you, what I did simple linear regression. So I had this, it could not capture this particular thing, only this. So those things also add uncertainties to the estimate of lambdas. So this is how lambda changes with forcing agent. I'm giving you some examples. And this is a latest work I did with my master's student, where she wanted to look into the impact of aerosol direct, all the aerosols, but let's just look into the direct effects and the indirect effects. So people know, right, what are aerosol direct and indirect effects. So good. So what she did, she increased the direct effect in some of the simulations and increased the indirect effects only in some of the simulation. You can see the lambdas, the slopes are very different. And only in case of this red one is somehow they are parallel to this 2 time and 4 time. So this is another example of like how forcing agent can change the lambda. And that's why lambda is so uncertain, and it's very important to work on that. By the way, like I just wanted to tell you, she has done many simulations, but one of the major thing that we all were thinking was that these simulations were done in a coarse resolution model, which is a 200-kilometer resolution model, or maybe more, I guess. So you could imagine, I mean, like how computation could be a challenge, you know. Had this been in a lower resolution, the results could be slightly different, right? The values could be slightly different, the slopes. Here is another example with the same black carbon, but I wanted to show you the spatial maps. You see, this is the radiative forcing from double CO2. This is the radiative forcing from 60 times BC. So whatever BC concentration is there in present planet, same thing, just increase the emission amount. So if you do that, the forcing is very different. But see the surface temperature change, the global mean, they're same. So this tells you that how, yeah, please. Why 60 times? To get, I was trying to check how much I should increase BC to get a CO2, because people say CO2 is the most important thing, right? So, but I wanted to check how it is different compared to black carbon, because black carbon is an absorbing aerosol. It also warms. So, but see, you have to increase by 60 times. So compared to CO2, although it is locally, it has a significant impact, but in global sense, it is much weaker than the forcing from CO2. Okay. So that's why it was 60 times. But I have tried several other values as well. And the other thing that came to my mind was, now just look at these two pictures. The global mean value is same. Okay, forget about the second digit. You cannot measure until second digit. Okay, it is really difficult because it's a global mean number. So both of them are 4.1, but you see the spatial pattern. So they're very different. So this could also somehow, you can also connect this difference in the spatial pattern to the feedback, because finally feedback is kind of the ratio of this and this. Okay, in a very simple manner. And that's how I went into this notion of how lambda changes with time. It must be there must be something, and then this concept of pattern effect came. Okay, how the spatial pattern. Now I'm going to show you here. So this is the dependence of lambda over time, on time. So if the pattern, so people have been using the historical period to, constrain lambda. I mean, constrain the climate sensitivity through lambda. But now if you see so I have done the SST anomaly, Kelvin per century, okay, only the trend from 1871 to 2017. So you see there is a cooling trend in the East Pacific, but a warming in the West Pacific. And very much warming here and a significant cooling. But again, I mean, this is, as I said, this doesn't capture, this model or any of the models doesn't capture very detailed physics of what Vishak was talking about. So these are, both of them are coming from models. So I'm also not sure whether this would be the right thing. There could be other small coolings here as well. Okay, so that is another challenge. But if you just compare from this model, the 1871 to 2017 period, and above 4 times CO2, which you can imagine that the future climate will have a pattern something like this. So you see, the Eastern Pacific is much more warming faster. But here it is the opposite. Now, so I pose the thing that if the pattern in the historical period is different from what it would be in future, then constraining ECS based on energy budget would be biased through this period, right? It will be biased, right? Because we are using a different pattern with different kind of climate to basically calculate lambda. And that's why maybe the models are failing to give, I mean, we are failing to get the right. And so this is one way to basically reduce the uncertainty. So this is another thing. So if you consider only the recent period, 1980 to 2017, they are different. Very different. Cooling, you see cooling. But this is only 2017. So I could do only until 2017 because I was doing just after maybe 2019 I started, 2019 beginning. But if you consider maybe from now to this year and next 2-3 years, we might see also a slight warming in this side, okay, because this El Nino thing is coming and then this story is coming up. So this is one thing. So now if you take care of all these patterns and try to reduce the uncertainty, so I've done that, and see what I have done here, this curve, the black one, this Gaussian distribution is from the AR6, okay, and this is only uses the historical warming thing, okay, not the other lines of evidences. I'm working on only the historical lines of evidence. So this is coming from AR6. So now if you add this particular pattern effect, this thing, that basically lifts this black, this black to this point. And when it comes here, it matches with other lines of evidences. So this was a proof that, okay, adding this particular thing is good, okay, it is beneficial for us. But there are other, uncertainties and uncertainties associated with it. So what has been done by people was, you force this model with the historical data, observed data, okay, but different groups around the world, they make their own observed data because they have observation at particular, you can put a thermometer at a particular location, okay, but in global scale the temperature could be slightly different somewhere else. So they use infilling methods, statistical methods to infill the whole globe. So that also comes into picture, and that's why when they use only a particular data set, they see that the pattern effect that they were considering to update the ECS estimate was slightly higher or lower. Okay, it was a different number. But when you consider all of them, so that this particular red line considers several data sets and several things. When you have this, it only slightly improved the ECS estimate. So again, there was a huge debate that it downgrades this yellow dot. Okay, so this I have been working on this presently. So I wanted to show you that how lambda changes with time and how it can basically affect all these distributions of sensitivity. So now I'll change the gear, okay, a little bit higher gear. So now I'm going to show you another simple model and how you can use such simple models to address problems, okay. So this is a 2-layer model. The first, this layer considers at the heat capacity, C considers atmosphere, land, upper ocean mixed layer, and CD considers the deep ocean, okay, and TD is the temperature of the deep ocean, T is the temperature of the mixed layer, and gamma is the coefficient which determines, because there could be a temperature gradient, right, T and TD, which is there, right, we know all. So that defines how these two layers will interact. So this gamma defines that. So it is the heat exchange coefficient between these two layers. And the equations look like this, okay. And this was first, again, it came from Hasselmann's fluctuation distribution theorem and developed here, and we have used this. We have also developed, we have used few things here, change few things. So now this is the observations which I have shown you from the IPCC, where I have shown you through 4 data sets. Again, here 4 data sets I have used, and I have plotted the historical warming from 1850 to 2017. Yeah, 2017 or 2019, I don't remember now. So 2017 most likely. And see the then GCMs when it was available with several ensemble members. What I did, I took the mean of all of this ensemble members. I've considered IPSL, CESM, MPIESM, and see the models are doing pretty good job. Okay, but in some cases, as Vishal has pointed out, they are also tuned. But the tuning takes place at a very low level of abstraction. Okay, it doesn't basically tune everything. Only there is a single target. Now, it may happen that some model targets to tune their system, their GCM for the historical, to produce historical warming, but it is doing a very bad job in simulating something else. This can happen. So what you tune, that is also an art. But anyway, so here I wanted to show you the models are doing pretty good job, okay, the GCMs in capturing. But there are certain things with certain models. For example, here you see the deep is for a long time, but the observation doesn't show that. Okay. And now I have my model, 2-layer model, okay, and which is this orange, just 2-layer, okay, nothing fancy is there. You can see nothing fancy, just 3-4 parameters, and see how good it is, the orange one. The only thing it is not doing that the recovery from the volcanic eruptions. So there is a volcano, it takes a bit more time to come back. Okay, and also I have done maybe 100 or 150 or 200 number of simulations with different things, and so that shows the gray, and it is well within the at least the models and also the observations actually. Okay, so now coming back to the real issue, so you see here this shaded place. This was the period from 2000 to 2012. Okay, and lot of people say that there was a lot of media which said that there was a hiatus, there was a pause in the warming. So like people like Trump and others, they said, is there a global warming? Because there is no, I don't see it, the climate skeptics. So now what I have done, I have calculated the observed temperature trend from 2000 to 2012 from different assessed observed data sets. Kobe 2 crew, which shows 0.16, hat crew T 0.14, hat crew T 4.6, 0.08. So this, if someone uses, no, I will use only this one, he is definitely a climate change denier, okay? Because here it shows no change at all, but it has also missing values. There were not all the points in the globe were not considered when you calculate this, when they have calculated their data, given their data. So this is another data set which shows you 0.1. Now, if you see all these models, they range from 0.26 to 0.14 to 0.26, very high value. So the models were not saying that there is a hiatus. So what was going on? So a lot of people worked, and my 2-layer model gave 0.14. Again, closer to Kobe 2 and had crew T4. This one was. But the debate was why there was this high, why what is happening with the models, why it is not showing you this low values, this pause in the warming. So this magenta, it is completely paused, but this is hat crew T4, 6. So now there was a lot of debate, and some said it is the errors in the external forcing, not in the models, but the forcing itself was wrong that you are giving to the models. So those papers are, and some say coverage bias was there. It was the problem with the hat crew T 4.6, which says that no, all the points are not covered. And the present consensus is that it is the internal variability of the system that basically both from the ocean heat uptake as well as TOA energy balance, which can cause such hiatus periods. Okay. Now, what is internal variability in a very brief way? Someone also pointed out. So now, if you, so this is MPISM Grand Ensemble. So they have a lot of money, very good supercomputer. So they have done this historical simulation for 100 times with different initial conditions. So now you can see this shows the weather, but the overall mean is this black one. Sorry, the brown one. And the black is the hat crew T4 data. So the model is basically doing a good job, and this is basically you can consider to be the uncertainty because of the internal variability in the system. Okay, and these oscillatory patterns are difficult to predict but not completely random. Hence, we call it quasi chaotic system, our climate system. Now, coming back to the thing that I wanted to tell you. So this paper said if the hiatus is because of internal variability in the system, then can we say in future whether the hiatus kind of periods will increase or decrease? Okay, they posed this question. And then they say that the decadal global temperature variability increases strongly with climate sensitivity. And they did very good analysis, lot of analytical work, lot of modeling. And then they showed that you see, this is HADGEM2 ES, this is a GCM, and the sensitivity is very high. But these are all CMIF5, AR5, okay? So 4.6 Kelvin. And they took another model, GISS, which is 2.11. And they say that, see, the variability is much higher in a high ECS model. Okay, 5 minutes. Okay, so and now if you plot the decadal trend, okay, the distribution, so it simply says that the model which have higher sensitivity has higher internal variability, which means that the hiatus kind of period will be more in such climates. So now again, it becomes very important to know what is the lambda. See, otherwise, how are you going to say whether there will be hiatus or not? But you know when I was doing some analysis with my two-layer model, I find that this was not the case. Okay, and this is what we answered in this particular thing. That what we did, we used the two-layer model, and we showed that as you increase. So I have run the two-layer model because it's a simple model. You can run many times. Okay, with different sensitivity, you just make the sensitivity of the model to different values. So for this different ECS values, I run the model. And I showed that the distributions, the decadal trend distribution, they change. Okay. The first thing is that the distribution widens, okay, as you increase the ECS, and they shift towards the right. And the shifting is faster than widening. And that tells you that the probability of seeing a decade, hiatus period, I made 0.1 Kelvin per decade because this was observed in the observations. So I made that threshold and calculated the probability of having such events with different ECS wall, different sensitivity wall, and it shows that it basically decreases as you increase the ECS, which is kind of denying their thing, but they have considered the CMIF5 models, which are slightly older version. So I proved, so now this is a two-layer model. No one will believe, okay, because this is a simple model. So then what I did, I used the CMIF6 models. I will avoid the reason, maybe you can come and we can talk about this, why that was happening. Basically, it is the deep oceans memory, which is not modeled in properly modeled, but some of the models do a very good job, which has very high, this value, the ratio that we have calculated here. Then I showed what I did, I used the CMIF6 models and showed that indeed the trend of the force trend, this is the force trend, okay, the shifting of the distribution is plotted here, and this is the variability of the distribution. So after a certain point, it gets saturated. And this was only possible in the CMIF6 because there are models in CMIF6, very good models in CMIF6, which has very high ECS. And you can basically use that kind of thing to do it. And this also basically, you can use this emergent constraint idea to basically constrain the ECS. So this is another way of constraining the sensitivity that I showed you. So parting thoughts. So we have looked into Earth's climate system consists of 5 major components, and climate change means each of the system, if it changes, it affects the planetary energy budget, hence the temperature. So climate change, it is, you cannot say that climate change is there in atmosphere. Okay, that is not a good sentence. So avoid such sentences. I hope now after this 2 lectures, you will know that. So we looked into climate change, what is climate feedback, different ways of estimating them, different ways of constraining them, and how it is, how important it is to constrain it or estimate it. We have looked into simple models to complex GCMs, how they are used to build our understanding, particularly the simple models, okay, and the nature of climate feedbacks, why it is a hard problem to bound the climate sensitivity, and how ECS has evolved over time, how we should be working on it. And finally, I have shown you how a simple model can be used to even counteract the results from a nature paper, okay. With this, I'll thank you all for giving me this opportunity.
Are there any questions? We have time for them. You might want to raise your hand. I'll quickly run and give you mic. Yeah, others might want to raise hands so that I know where to run.
In the graph of the mean surface temperature. You said that one of the dips was explained by a volcano.
No, not one of the dips. So all the dips, if you see, this model was not doing a good job here. So there was this huge volcanic eruption, and this model was not able to pick this up. Okay, see this GCM or the observation. There was a delay in coming here. Okay, also here, also if you see, this is, so yeah, here is the Pinatubo. So there was a lag.
So
And again, it is because of the deep ocean. I have considered 100 meters, I guess. Even the deeper ocean is 100 meters. And the shallow ocean is 50 meters. 200 meters and 100 meters, 50 meters. Yeah.
So are the dips like spurious, or are those, do we know the
No, they are not
explanations?
spurious, because this is a ensemble mean of several runs.
Huh.
Yeah. They are not
So we
spurious.
know the explanations for
Yeah.
this.
Yes. And that's why they are falling exactly at the right time, right? Wherever there is a volcanic eruption.
Other questions? Yeah, you might want to raise your hands early. Yes, I know.
You can work on several things here. Okay, I have, for example, included both E and psi, E and gamma. Many things can be done here with this model.
Hello, sir. Thank you so much for your talk.
Hi.
Sure. Yeah. So I have a question which is related to your previous talk, actually. So in the Manabe's paper, I have heard one term called as convective adjustment that he uses there. So I just wanted to physically understand, like what he says is that when that adjustment takes place, so if some...
No, what?
Actually, my question is related to your
No,
talk,
I heard the last line. What did you say?
that in that convective adjustment he does in
Yeah,
the
yeah.
Manabe's paper. So I think he, if the critical lapse rate crosses some value, he adjusts it to some particular threshold value.
Yes.
So I was not able to understand what physical phenomena is taking place that is making that adjustment, like physical representation, like how physically things are happening.
We can talk about this. Yeah.
Sure.
So it is mostly he has fixed it to 6.5 Kelvin.
Something like that.
Yeah, something like that, right? Because that is the value that he say that is the only thing that I can do. Now the model, I have to see, I have read the paper really long back. I have to see where you are referring it to. Yes.
Sure.
Yeah. Because it is a simple single column model. So it might happen that the model is giving a very large number. So he has to adjust it to 6.5, right? Yes. Okay. We will talk more. Yeah.
Hi, this is very interesting. So I have a question about the deep system. The deep ocean temperature also has the same trend of this trend.
No, I have not plotted that.
Okay. So what is usually the deep ocean temperature trends are in the whole climate change scenario?
No, yeah. Tell me again.
I'm saying, what is the trend in the deep ocean temperature?
I don't have a picture, but there must be something in the IPCC report. But
Okay.
what people do is the sea level rise only. They never plot the deep ocean TD, and that's why I guess I also did not do it.
Okay.
But I know that I can use this TD to work on sea level rise.
Okay.
Thank you for this. Yeah.
Hi, thanks for the talk. Not a difficult question, but how would you improve this 2-layer model? Like, do you have any proposals for how do you?
The people have already proposed. People have tried. So there is this paper who have tried several layers. Okay, but it doesn't help much. Doesn't improve the things much, as we have seen with increasing the number of layers in the radiative equilibrium model. But it does improve in this case. But it is not that significant improvement. The other thing is that this is only, top bottom. You can also make it 2-zone model or 3-zone model, because let's say you want to, it all depends on your question that you want to address. Suppose you want to also include land. What do you do? Okay, explicitly. So in such cases, you can use 2-zone model, or 3-zone model or 2-zone and 1-layer model. So such things can be done.
Thank you.
Yeah, I'm looking forward to people with this thing so that I too can work. Yeah. Yeah, but there are avenues to go in that direction, improving this one. By the way, I must tell you that this is the same emulator which IPCC has used this time in its report AR6 to predict everything, to show you all these graphs, because it is very difficult to run the GCMs and use only the GCMs to give the future projections, and nobody wanted that because they wanted to include, as I said, various lines of evidences. So they use this emulator and adjusted different parameters based on different lines of evidences.
Hello, sir. Sir, do you think all of these simple models for not just the climate, for various stuff, for example, Vishal sir showed us simple models for the monsoon. Do you think these simple models, we can use those to do anything else other than to improve our understanding of the climate? Like,
I mean, other than, yeah, why not?
because
I mean, if
obviously
you
they
improve your
cannot
understanding,
explain.
then again you add something to the GCMs, right?
But then
I
the
mean,
GCMs don't really use exactly these equations. Those are much complex, right? Much more complex.
yeah, but physical understanding comes from here only, right?
Yeah.
So, but when you say, is there any other, are you saying that can you basically predict something?
Yeah,
Are you saying that?
Yeah,
You
something
do,
you just pointed out.
Yeah.
It cannot explain the extremities very well. That's a common trend with these simple models that I've noticed.
Yes, it will fail. But maybe, yeah, you can, I mean, we can work on that. What to do here so that it can do it. So see, this is the problem that you are posing, and we can sit together, work and write a paper, right?
I see there are a
Good,
couple of
thanks.
questions online. We will see them here, but if the attendee is available, please unmute and ask your question.
Yeah, hello. I saw river runoff listed as one of the factors which influence. So how exactly is river runoff included as change in mean discharge or change in non-stationarity of pattern, stream flow?
How does river runoff enter as change in mean discharge?
Yeah, Indulekha, we couldn't hear you, but we are reading the question on the screen.
Okay.
Where, so are you talking about how does river discharge is taken care in the GCMs?
River runoff was listed as, among one of the forcings in one of your slides. Yeah.
River was listed as one of the forcings?
Yeah.
I guess they could be forcing for ocean thing. If you have river runoff, you have a little bit fresh water, right, on top of the ocean. So on the sea bed, basically on the sea. So that might change locally, but I'm not sure how it will have it. Yeah, but yeah, it could. You can see a signature in the OLR as well, in the top of the atmosphere flux also, net flux as well, but only over that region. If I remember seeing a slightly different, pattern just over Bay of Bengal, on the top of Bay of Bengal, because you have a lot of river runoffs there. So it does have some impact on the forcing. So it could be only in that way that river runoff is a forcing to the system, but it is mostly significant on local scales.
One thing which I have heard is like putting a lot of dams can change the quantum of water that flows into exactly Bay of Bengal, and it can change the salinity. That's one thing I have heard. The other part of the question is, I mean, almost 80% of rivers which have human interventions on them, like dams, etc., they show change in the pattern of discharge. So that's the point I was asking. Is it the quantum of discharge which enters or the pattern of discharge? Anyway, it's...
At this point, yeah, quantum of discharge or the pattern. So intermittent, you stop the river water, and again suddenly you open the dam and
Yeah.
you allow it. Such
Lots of
that would be
variability
very. I
happening.
mean, we do it in what time scale? Maybe in few days. I am not very much into that.
No,
How
no,
many?
no, no. Like
Yeah.
lots of perennial rivers have gone intermittent. Like flow days have reduced by 1/3. Like what had been perennial has become flowing only for 200 days and things like that. So that's why I asked, is it
Yeah,
a quantum?
definitely. That could be considered as a forcing for very local scales. You know, as I was saying, on local scales, this thing will matter.
It is
Definitely.
listed in one of your slides among biogeochemical of all those.
There is a nice paper written on this by, I think, Jaffer and Vinay Chandran. They, in a GCM, kind of remove freshwater influx from Amazon and important rivers, and they check the response. I don't remember how big was the response, but that's the paper to check.
Yeah.
If I may add.
Yeah. No, that is right. I guess I was also pointing to but she's also saying that you have this number of, I mean, because there is less
smaller
rain,
time scale.
so the dams are having less, water, but so the frequency at which you open the dam and close, that also, does that have an impact? But yeah, that is, I guess, very in local scale that could have. So I have recently reviewed on paper on Nile River, and the response was really, I mean, the impact of that. So Nile River is fed mainly by the the rain that happens in one of the near the mountains, which is south of Egypt, and so they were looking into how much rain has reduced over time and how that has impacted the Nile River. But I did not see much of an impact there. So yeah, I was not very happy with the paper. But yeah, but there is an impact. I have seen that, but the magnitude is really less because they have considered the entire basin, not just Egypt, but the entire basin in that location.
Thank you.
Yeah.
Thank you. Are there any other questions? Maybe we can take one more. Yeah, maybe if not, maybe everybody's waiting for lunch. So let's thank Angshuman again. And thank you.